Okay, good morning, friends. In the last two classes, we discussed about plant and water relationships, and also we discussed about mineral nutrition. And in today's class, we'll discuss about the enzymes. So, what are enzymes, and how do they function, and what are the factors that influence enzymatic action, etc. We'll learn in the next 45 minutes or so. So now, first of all, now what do you mean by an enzyme? I hope this term is quite familiar to you. You came across about this term enzyme from 10th class onwards. You learned about them in 10th class and also in intermediate. There was a little bit detailed study of enzymes that is being covered in intermediate. Now coming to our core syllabus of this 6th sem plant physiology. Now in enzymes, so enzymes are nothing but proteins. All enzymes are proteins, but remember, all proteins are not enzymes. This is a famous, sentence generally we use when we learn about enzymes. Now, enzymes are otherwise called catalysts. Now we have, in chemical reactions, the, chemical reactions activity is being regulated by certain specialized metals or certain compounds. They are called catalysts. Now, catalysts generally, they enhance the rate of reaction. Now, so also in living organisms, a number of biochemical reactions take place in all living cells. And these chemical reactions are more specifically biochemical reactions are regulated by certain catalysts called enzymes. So they are otherwise called biocatalysts, not inorganic catalysts. Generally, inorganic catalysts generally they take place at reactions take place at higher temperatures, maybe more than 90 or 100 degrees centigrade in chemical reaction. So whatever, of course, you are familiar with, various tests you have done in chemistry lab, wherein you add various things and observe the precipitations and other things. Generally, for performing certain chemical reactions, generally we make use of spirit lamp or a lamp, that is LPG lamp or whatever the case may be, or Bunsen burner, etc. So generally, to hasten, to speed up the reaction, generally we heat them. So while heating, what is happening? You're taking that components to higher temperatures, maybe more than 70, 80 or 100 degrees centigrade. But living beings, what is our body temperature? Our body temperature is around 37 degrees centigrade. So almost all the reactions that occur in our body occur at body temperature, that is around 37 degrees centigrade. So generally, it is a common thing, generally if you keep any, for example, vegetable or any food stuff, but especially in the summer, what happens? So what if you cook, maybe your dal or anything this morning and you keep it for dinner, you will see some smell coming. So generally during summer season, so various, activities or reactions do occur. That is, in contrast to that, if it is a winter season, then generally even the things doesn't get spoiled. Foodstuffs doesn't get spoiled even after 24 hours of their cooking. So generally at higher temperatures, what is happening? There is an enzymatic activity, especially there is a putrefaction or spoilage. Spoilage is done by what? various bacteria or fungi, etc. So in them, so there the reactions are taking place at room temperature. So room temperature, it is around 29, 30 or 35, 38 or 40 degrees centigrade, because higher temperatures generally the enzymatic activity will be more. If the enzymatic activity is more, means what is happening? The bacterial activity is more, bacteria multiply more. So thereby their action takes place and thereby they spoil our food. See, for example, it is not an exaggeration. See, so you take food. When you feel hungry, after a gap of 3 to 4 hours. So during these 3 to 4 hours, what is happening? Whatever the food you take is getting digested in your digestive system. For the digestion to take place, there is a need of various chemicals, including your enzymes. So we need various types of enzymes. Of course, think, for example, you don't have any enzymes in our body. If you take food, it takes more than 3-4 days for the digestion of the single meal if there are no enzymes. So that means in the presence of enzymes, the biochemical reactions take place at higher pace, and the substrates get converted into products. So such biocatalysts that enhance the rate of biochemical reaction, wherein converting the substrates into products, are called enzymes. Now the enzyme, the first enzyme that came to our knowledge was with the discovery of, or with the separation of zymase by Edward Buchner. Edward Buchner's, was the first man to isolate zymase. Zymase, that is responsible for our fermentation. Fermentation is done by your zymase that is extracted from yeast, a fungus. Since then, a number of people worked on these enzymes, and especially the path-breaking discovery was made by, James Sumner. He isolated, various enzymes, especially urease. He isolated urease from jog beans, and later on it was, Northrop and his associates. After doing a lot of research on enzymes, they finally concluded that all enzymes are proteinaceous in nature. That means enzymes have, a chain of amino acids. So amino acids linked by peptide bonds, making long chains of polypeptides, and these polypeptides in turn make proteins. These proteins are nothing but our enzymes. Now coming to, we have certain properties. So far, thousands of enzymes have been isolated or known to scientists. Now, as on today, we have more than 2,500 enzymes known to us. Now, you have to remember the enzymes are more and more specific. A given enzyme regulates only a given substrate. That means each reaction is regulated by a given enzyme. A single enzyme cannot do many biochemical reactions. Each biochemical reaction is regulated. That means for each reaction, there is a specific enzyme. This we call enzyme specificity. This is called enzyme specificity. So first you have to remember regarding the characteristics, all enzymes are proteins that you remember, but all proteins are not enzymes. Now enzymes are nothing but long polypeptide chains. Now enzymes have high molecular weight. Their molecular weight ranges from 10,000 to 1 million Daltons. Now generally on the surface of the enzyme, there are certain specified areas. They are called active sites. Now these are the sites to which a substrate binds and ultimately get converted into a product. Now you have to remember one thing, enzymes never undergo any change. They facilitate for the conversion of substrate into a product. At the end of the reaction, they get themselves liberated from the product, and they are capable of doing the same reaction for n number of times. So they never get modified. They never get attached to the end products. They get liberated. They have the ability to perform the same reaction, enzymatic reaction, for n number of times. There is no loss of enzymes. This is also another very, very important. Now, one more characteristic you have to remember regarding enzymes is that enzymes have high turnover number. What do you mean by turnover number? So even under short notes, you may get this enzymatic turnover number. What do you mean by that? Enzymatic turnover number means how many molecules of substrate get converted into end product by a single molecule of enzyme in 1 second time. So in 1 second time, one molecule of enzymes capability to convert how many number of molecules of substrate into product. This is its turnover number. The turnover number will be maximum. It will be in thousands and it will be in lakhs. A small, say for example, if you assume blackboard size, that is substrate. You put a dot with your chalk. That becomes your enzyme. So because enzymes are proteins, they have large surface area, long chain surface areas, and they have a primary and secondary and tertiary structures. And in making tertiary structure, they have a number of crevices or loops. Those specialized crevices and loops have what we call active sites, to which the substrate comes and makes a bonding and form what we call enzyme substrate complex. And this enzyme substrate complex later on gets converted into enzyme and product. After the formation of product, the enzyme gets liberated and again it starts. So this is how a single molecule of his enzyme is capable of converting millions of molecules of substrates into end products. This is, you have to remember, they have high turnover number. And another important thing you have to remember that enzymes are quite specific. I told you a single enzyme performs a given reaction only. And the other thing is generally they are thermolabile. That is, they are sensitive to temperature and also pH. So for each enzyme, there is an ideal pH and temperature. But to take on an average, so almost all enzymes are highly active between 25 and 35 or between 25 to 38 degrees or so. Below that or above that, the enzymatic activity is at. So it has been calculated that for every 10 degrees, the enzymatic rate gets doubled. This is what we call Q10. If you lower the temperature by 10 degrees, it gets halved. If you increase the temperature by 10 degrees, it gets doubled. This you have to remember. Then coming to pH also. So pH also, generally some enzymes are active in acidic pH and some are in basic pH, but most of them are active or do maximum performance, give maximum performance at neutral pH, that is 7 pH. So these are some of the, characteristics of enzymes you have to remember. Then we move to nomenclature and classification of enzymes. See, when enzymes were, very few number of enzymes were known, the conventional method of naming was by adding A's to ASE suffix to the substrate. Then it becomes, for example, sucrose is the substrate. The enzyme that converts sucrose into glucose and fructose is what we call sucrase. Amylum. Enzyme that acts upon amylum is amylase. Protein, protease, lipid, lipase. Just by adding ASE as a suffix to the substrate, that becomes the name of the enzyme. But this was okay when the number of enzymes that were known to us were limited. So by adding simply AS, ASE, you can name a given enzyme. But there are, so as the number of enzymes that came to our knowledge became known, so this did not work. A lot of confusion arose. To avoid this, so there is another way of naming. One is based on what we call, first is based on adding substrate ASE to the substrate. Sucrase, maltase, amylase, etc. The second category is by knowing the type of enzymatic activity it performs. For example, oxidases, reductases, dehydrogenases, decarboxylases, phosphatases, aminases, transferases. I think you are getting it. So here, based on the type of reaction it is performing, reductases, they reduce. Addition of hydrogen is reduction. Addition of oxygen is oxidation. Removal of carbon dioxide is decarboxylase. Removal of hydrogen, dehydrogenase. Phosphatase. So like this, deaminase, amino group removal. So like this, based on the type of reaction that a particular enzyme performs, you can also name them. But there are certain exceptions. For example, ptyalin. Ptyalin, I hope you heard this. Ptyalin is present in our saliva. Ptyalin, no relation to either to the substrate where it acts or type of reaction it does. There are certain cases like ptyalin, trypsin, pepsin. There is a certain exceptions. Now this is how enzymes used to be named. Now by 20th century, second half of 20th century, that is 1960s, number of enzymes that came to be known became more thousands. So it was found to be very difficult to name them and to classify them. So to avoid this, so International Union of Biochemists, IUB, in 1964, all famous biochemists of the world in a congregation, in a biochemical congress, they resolved and commissioned an association called Enzyme Commission. That Enzyme Commission offered a scientific method of naming enzymes. This is what we call enzyme nomenclature. But whenever I say nomenclature, I think our botanical nomenclature comes to your mind, wherein our Linnaeus method of naming plants, generic name, specific name, two-worded name, etc., etc. I hope you know that. But in contrast to that, here in enzyme nomenclature, here numerical classification is used. That is, they give a number like, for example, your vehicle numbers, vehicle numbers, your scooters or your cars, we have, numbers. So also here we have numerical classification. Now this numerical classification, this enzyme commission grouped all the enzymes that are known to us into, 6 groups, large groups. 6 large groups they were divided into. They are what we call oxidoreductases, transferases. So they were oxidoreductases, transferases, hydrolases, lyases, isomerases, synthetases. So six groups. Six groups are six categories, six broad categories based on type of reaction. Oxidoreductases, oxidation reduction reactions. Then transferases, transfer of groups, functional groups, maybe amino group, carboxyl group, or phosphate group, etc. Then, lyases. Here, lyases, the breakdown. Either addition, simple molecules are added or breakdown. So this is lyases. Then isomerases, isomerism, left and right, isomers. So isomers are included under isomerases. See, for example, isomers. Good number of isomers are there. For example, ribose 5-phosphate isomerase, epimerase, dihydroxyacetone phosphate. So the trioses. So, for example, say I think we'll learn about that, if you remember the glycolysis process, wherein glucose gets broken into two pyruvic acids at 10 steps. Each step is regulated by a given enzyme. Now, so like this, isomerases, then lyases. So ligases, here synthesis, ligases. So wherein ligases, wherein small molecules, for example, amino acid plus tRNA plus ATP, amino acyl tRNA. This is what we call ligases. Then last one is what we call synthetases. So synthetases is another one. Ligases and synthetases are one and the same. So you have to remember six groups. What are they? Oxidoreductases, transferases, hydrolases. Good example for hydrolases is all our digestive enzymes. So whatever the enzymes that are there in our digestive system, they fall under what we call hydrolase. See, hydrolases are active, do reaction only in the presence of water. Hydrolases. So oxidoreductases, transferases, hydrolases, ligases, isomerases, and ligases or synthetases. These are the six major groups into which all enzymes are categorized. Now each enzyme given a 4-numbered nomenclature. So here name has 4 numbers. For example, these 4 numbers, first one denotes class, second one denotes subclass, third number denotes subclass, and the fourth one is its serial number. So here 4 lettered or 4 numbered name. 4 numbered name. First denotes its class, second denotes its subclass, third denotes its subclass, and the last number denotes its serial number. See, for example, we have what we call 1111. One, oxidoreductase. So oxidoreductases, so it is nothing but alcoholic dehydrogenase or alcohol NAD oxidoreductase. 1111. So alcoholic dehydrogenase or alcohol NAD oxidoreductases, it belongs to first class, first subclass, first subclass, and the serial number 1. Okay, so this is about what we call nomenclature and classification of enzymes. So now, then we move to enzyme structure and mechanism. How do they act or how do they work? How do they regulate the chemical reaction? See now, so the general enzyme structure, I already told you, enzymes are proteins. They have long chain of amino acids which are linked by peptide bonds. They may be linear, they may be folded. This folding, what we call secondary structure, or spiraling, that we call tertiary structure. So generally, enzymes are active in tertiary configurations. In tertiary configurations only, we have loops and crevices to which they are nothing but active sites to which the substrate comes and binds and ultimately gets changed into a product. So now, so first of all, you have to remember three important terms. One is substrate, the enzyme, and the product. Substrate, the initial substance. So initial substrate comes and binds with enzyme. This we call, so S is substrate plus, right, what we write E. S means substrate plus E is enzyme, then arrow mark, then comes what we call substrate enzyme complex. Next step, a product plus enzyme. So substrate enzyme complex cleaves or gets converted into end product plus enzyme. So this is how enzyme works. So now, more specifically speaking, I told you enzymes have, long chains and configurations, loops and crevices, and these are called what we call active sites. Now, these are the sites to which the substrate comes and binds. So now, to explain the mode of action, how enzyme works, two important methods have been put forth. One is what we call lock and key method, and the other is induced fit theory. This is also very important for you as far as examination is concerned. So generally, what is the mode? What are the theories that explain the mode of action of enzymes? There are primarily two important theories. One is lock and key theory. The other is induced fit theory. Lock and key theory, this is an old one put forth by Emil Fischer, and it was supported by Fields and Woods. Now this, I'll tell you, lock and key. You know the lock, you know the key. So here the lock means lock is the enzyme, key is the substrate. So there is a specificity. For each lock to be opened, you need a specific key. So for each lock, you need a specific key. That is, there is a close resemblances between an enzyme and a key. So enzyme here is like your lock, key is your substrate. So for example, in a cell, there are lot number of enzymes available. There are lot types of substrates available. So each substrate recognizes its complementary active site and comes and binds there. So this relationship is what we call lock and key relationship. So it shows that lock is fixed and key is fixed. There is no scope for any change. But later on, another important theory was put forth by by another important person, and that is what we call Koshland's induced fit theory. This Koshland's induced fit theory says that the enzyme, its active sites and enzyme's configuration is not quite fixed. It is rather elastic. He compares, like your gloves and hand. See, for example, you have gloves. Gloves don't have any shape. If you insert your fingers, it resembles your palm. So according to Koshland, he says that your glove is like your enzyme. Your fingers are your substrates. So fingers come, and when the fingers come, that is when the substrate comes, the enzyme makes certain adjustments. When it comes and binds, it changes its configuration a little bit. So there is scope for some modification. A little bit modification is possible. Configuration changes. So when a substrate comes and binds with an enzyme, and this binding may be loose a bit. So generally, maybe covalent bonds may be there, loose fitting will be there. Some cases, this bonding will be very tight and irreversible. Of course, we'll learn about them later on. So here, but you have to remember, so a little bit scope for change is possible in Koshland's induced fit theory, but this is only to a certain extent. He says that you cannot insert your right hand into left hand glove. So also left hand cannot be inserted into a right hand. So this is what we call induced fit. So induced fit theory says that substrate comes and induces some changes in the structure of the enzyme, and thereby it fits and ultimately gets converted into a product. This is what we call induced fit theory and lock and key theory. Okay, now we will learn about factors. What are the important factors that regulate enzymatic activity? So generally, you have to remember 4 important things. One is, of course, temperature. The other is pH. I already told you, as you increase the temperature, the rate of enzymatic activity increases, but only up to certain temperature. Thereafter, the rate of enzymatic activity falls sharply. Why it falls? So it forms a bell-shaped curve. It increases, then stationary, then it falls. So is the case with pH also. Certain change an enzyme can accommodate, but at extreme steps, either too acidic or too basic, there is a fall in the rate of enzymatic activity. Say, for example, temperature, I told you Q10. When you increase the rate of temperature by 10 degrees, generally enzymatic activity gets doubled. But after 40 degrees centigrade, there is a sharp fall. You may ask me, why so, sir? Because I told you enzymes are proteins. If proteins get subjected to high temperature, they lose because they're enzymes. They get coagulated, they get denaturated. Hence, there's a sharp fall in enzymatic activity. So is the case with pH. Now we move to other 2 important factors. One is substrate concentration, the other is enzyme concentration. For example, to begin with substrate concentration. Say, for example, you have enzyme concentration is constant. If you increase the concentration of substrate, there is an increase, there is a proportional increase in the rate of enzymatic activity. But this, after some time, it becomes a plateau, then it falls. There is no further increase. Why so, you may ask? So, for example, enzyme is there. I told you on the enzyme we have so many active sites. So the substrate comes and makes a bond at the active sites. So when all the active sites of an enzyme are filled, so if you go on adding substrate, no change because no active site is left over. So hence, if then what happens? The enzyme concentration becomes a limiting factor. So that's why, to a certain extent, if you go on adding, increasing the concentration of the enzyme and substrate, there is a constant increase. There is a consequential increase in the rate of enzymatic activity, but thereafter it no change. So is the case with enzyme. So for example, you have substrate. If the substrate concentration is constant, if you increase the concentration of enzyme, as its concentration goes up, so also enzymatic activity goes up. But after some time, if you increase further increase in enzymatic activity, enzymatic concentration brings no change, means there the substrate concentration becomes a limiting factor. So what I mean to say here is temperature, your pH, your concentration of the substrate and also concentration of the enzyme determine the rate of enzymatic activity. Now finally we move to what we call inhibition of enzymes. Inhibition of enzymes. Now say enzymes, I told you they have active sites. Now this inhibition is called, so inhibition means enzyme, I told you there are number of what we call active sites. So these are the areas to which the substrate comes and occupies, and thereby it gets converted into a product. Okay. So now inhibitors are the substances that come and occupy the active sites of the enzyme. Thereby they make the enzyme dysfunctional because the unnecessary, unwanted things are coming and occupying the active sites. See, for example, you are traveling. You have reserved your seat. If some unscrupulous elements come and occupy, if there is no police, what do? There is no scope. See, your seats are already occupied. There is no scope for you. So these are occupying, means they are inhibitors. They are checking your activity. Your places are occupied by unscrupulous elements. These areas of these active sites are occupied by unwanted substances. So these such substances which occupy the active sites and thereby reduce the functionality of the enzymes are called inhibitors. They check the enzymatic activity. So generally you have to remember inhibitors resemble the substrate. They mimic. See, for example, in cinemas, etc., dupes will be there. Dupe look like your hero or heroine. Very similar. So here also certain substances which mimic the original substance come and occupy. Thereby the enzymatic activity or the reaction in which we are interested gets hampered. So such substances are called inhibitors, and the process is called inhibition. Now these inhibitors are of two types, or inhibition is of two types. One is reversible inhibition and the other is irreversible inhibition. So irreversible inhibition means a compound which resembles your substrate comes and occupies that area, and they bind tightly. They become immovable and they never get separated. Even by using specific separation, dialysis, etc., also proves to be futile. So the inhibitors that cannot be even separated or removed by dialysis, etc., are called irreversible inhibitors. Like your poisons, certain poisons, say for example, certain things you take. Nowadays, all, almost all the substances, you are starting for your milk, etc., they are mimicked and they are, unwanted substances are added. They spoil your health. So here, irreversibles, they come and occupy your seat and they never go. They make the enzyme dysfunctional. So generally, we have a technique of separating the such unwanted things by a process called dialysis. Dialysis, I think, generally for patients suffering from, kidney failure, machines are there, dialysis machines. They filter your, deoxygenated your blood, and they purify it. So here also dialysis is a process that is useful in separating this unwanted inhibitors. So such inhibitors which cannot be removed by dialysis are called irreversible. Then reversible. Reversible are means they mimic your substrate. They come and occupy the active sites, but they can be removed by what? They make a loose contact. They make a weak bondage with the active sites. So by increasing the substrate concentration, say for example, you are there in your house, you are single, one or two people, for example, you and your wife or your father and mother are there. If a group of thieves enter your house and they overpower you because they are more in number, you cannot do anything. But if two or three thieves are there, if your inmates, your room, your housemates, your brothers, sisters, so many people, if you are 10 in number, then you overpower. That is, by increasing your concentration, by increasing the concentration of substrates, you can remove the loosely fitted unwanted inhibitor. This is what we call reversible. You can reverse the process. This is what we call reversible inhibition. Reversible inhibitors can be removed by increasing the concentration of the substrate. So this is what we call, so there are classical examples. These reversibles are again two types. One is called competitive and non-competitive. Competitive means they resemble. So here for the active sites, your original substrate and your mimicking substrate, unwanted substrate, come and compete. So for example, a good example for this is succinate and malonate. So succinic acid, succinic dehydrogenase, succinate is gets converted into fumaric acid by succinic dehydrogenase. So succinic dehydrogenase's activity is checked by a malonate. Malonate resembles succinate. So the active sites which are supposed to be occupied by succinate are occupied by malonate. So this is called competitive. They compete for the active sites. Non-competitives are that the non-competitive inhibitors, they do not resemble, they do not compete for active sites, but they make attachment to other than active sites. So by attaching themselves to the other areas, though they are not active, so they become a liability. You are not free. Something is clinging. So that's why, hence, their activity gets hampered. This is what we call, non-competitive. So non-competitives make what we call enzyme inhibitor substrate complexes. But enzyme inhibitor complex is formed in competitive inhibitors, whereas enzyme inhibitor substrate complex is formed in case of non-competitive inhibitors. So this is about your enzymes. So now I'll give you 5 minutes. Now you can raise your doubts. If you have any doubt, I'll try to clear your doubt. So now, if you don't have any doubt, then next class we'll discuss about the most important physiological process, that is photosynthesis. So in the next class, we have 3 classes in continuation. That is on what we call on 10th, on 11, 12, and 13. So on next Friday, Saturday, and Sunday, we have 3 classes wherein we'll study about the mechanism of photosynthesis. What is photosynthesis? What is light reaction? What is dark reaction? What are C3 plants? What are C4 plants? What do you mean by translocation of solutes, etc., etc. Okay. So if you don't have any doubt, now let me close this session and see you next week. Thank you for your patient hearing.